All right, welcome everybody. Today we are taking a look at the scenario of an object on an inclined plane. And we're spending the whole class on this particular topic because it's a new concept and I want to make sure we are spending the time to get used to it. So welcome Troy, welcome Taylor, welcome Spring, welcome Sophia, welcome Noble, welcome Luke, welcome Caden, welcome Joy, welcome Josiah, welcome John M and John F, welcome Isabel, welcome Hannah, welcome Gabriel, welcome Ezra, welcome Elizabeth, welcome Elijah Patz, welcome Elijah Crane, welcome David, welcome Chester, welcome Arlie, welcome Aaron. Troy asks, isn't the coefficient of static friction equivalent to the tangent of the angle that the object is raised to? Yes, and we will demonstrate that. Let's open with a word of prayer and begin. Lord, we thank you for this day that you have made. We ask that you would enable your people this day to honor and to glorify you in what we say and in what we do. We ask this in your son, Jesus' name. Amen. Okay, so let me just start here with a piece of paper. The diagrams that I'm going to be drawing out for us are similar to the ones that you had in the textbook for your reading, specifically on pages 198 and 199. So with dried glue, that's a very different scenario because things are stuck together, it sounds like. Is it friction? I don't think so, because friction, as defined all the way back in chapter number 5, you have friction where the molecules are sliding and bumping against one another. But if something's glued together, then you have a bonding together. So they're not sliding over one another. I don't know if chemical bonding is the accurate word. My guess is yes, because glue adheres chemically to different surfaces. But you don't have to worry about any glue related questions for what's it called, for this chapter. Could the bonding greatly increase the friction? I would say no, because the bonding erases the conditions of friction. Is it a physical bonding process instead of a chemical bonding process? That is an interesting question, because if you have glue between two surfaces, the glue, like glue on a piece of wood, it doesn't change the nature of the wood, but something is happening between two pieces of wood glued together. It's not a chemical change, but it's some sort of physical adhesion. I will have to research that more. All right, so there you have some box, and I'm going to contrast this with a scenario of some other box on a flat surface. Now, if you've ever looked at Velcro, Troy, it's just like those little thorns that hook into the fabric. And in fact, the invention of Velcro was inspired from those little thorns on seed pods in nature. So in the force of gravity on this box, we know that the normal force is in the opposite direction, directly opposite. And we've always said that it's equal in magnitude. So we've said in this scenario that the normal force is equal to the force of gravity and is therefore equal to the weight. Now in this scenario here, where we have the box on the incline, let's say that this box is sliding down the slope. And if this box is sliding down the slope, we still have the force of gravity behaving in this particular direction. And of course, the slope would be at some angle. Now, we've said that the normal force here, it does not behave the same as when the box is on the flat surface. Instead, we have the normal force like this, because the normal force, as you remember, comes from the surface the object rests upon. So that surface in this case is at some angle, and so therefore the normal force is also at that particular angle. And then for the force of gravity, which component of the force of gravity opposes the normal force? Okay, so when we look at the force of gravity and we break it up to dot, 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 and here, dot, 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 dot. Oh, I drew that at a bad angle. It really should have been something like this, dot, 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 dot. There we go. And then we have another arrow here. It depends on where you're defining your X and where you're defining your Y. But we have this as our angle. So this angle here is the same angle as this one over here. And as we're just looking at this, the force of gravity, we're talking about this component being equal to the normal force, because the box is not going up off the surface, it's not going through the surface, it's just staying on it. So in this case here, we would say that the normal force is equal to the force of gravity times the cosine of theta. So why is it the cosine of theta? If we turn the picture to look like this, and this is our angle theta, we're interested in this portion right here. This side is the adjacent side to the angle, which is why we use cosine. So F of n is not just automatically equal to the weight of the object, as in this scenario when there's no incline. When we do have an incline, the normal force is equal to the force of gravity times the cosine of theta. Does anybody have questions about this new relationship between the normal force and the force of gravity at an incline? Why is it cosine again? Sure. So cosine, sine, the definition of those things depends on the location of the angle. And when we have this angle here, this angle is the same as this angle. I'm not going to ask you to prove that geometrically or anything like that. But notice if we tilt the picture and we look at the angle, if we're interested in the value of this force, this side is adjacent to the angle. And then the hypotenuse here is the force of gravity. Was that able to answer your question, Hannah? The angle itself isn't equal to the normal force, it's the cosine of the angle. Not quite. So the normal force is equal to the force of gravity times the cosine of the angle. Because the definition of cosine, the cosine of an angle is equal to the adjacent side divided by the hypotenuse. And the adjacent side here was this particular value. And if we want to talk about this direction as the y direction, we could say that this is f of g of y, and the hypotenuse is just f of g. So therefore, you have the solving of the normal force. That would be this f of g of y is opposite in direction equal in magnitude to the normal force. And we can multiply both sides by the force of gravity to have the normal force equal to the force of gravity times cosine of theta. In this case, no, that force of gravity does not equal the weight. It's equal to a component of the weight. So I'll put this over here as force of gravity in the y direction. And then this one here, this is the force of gravity in the x direction. The book says Fn is equal to weight cosine theta. Yes, so remember that the force of gravity and weight are the same. So just because you tilt an object doesn't change the weight of the object, but it does change the normal force from the surface on the object. Thank you, Troy. So if you think about it like this, I think we all intuitively kind of understand this. Let me give you an example about what I mean. If we take some object with mass, just I'm using my textbook here. My hand is not really at an angle that's flat because my wrist isn't a perfect 90 degrees. So this is not a perfect right angle. But if you do this with your book, we can say, why is the book not falling further down? Well, we'd say like, well, obviously there's a force opposing it coming from my hand. And so the normal force from my hand is opposing the force of gravity. Again, that's the Newtonian perspective. But if I tilt my hand, you're going to feel less force that's being put on your hand. So my hand here, just because my hand tilted, it didn't change the weight of the book. The book's weight is still the same. But the normal force from my hand, it's now at an angle. So my hand is putting less force in this direction compared to here. And I think perhaps we may even feel that when we're lifting an object, and if you just hold it straight out in front of you, it can feel heavier, but if you like tilt it back a little bit, it doesn't feel so bad. So the force of gravity in the y direction here is a little less than the weight of the object because it's a component of the force. So for example, we could actually demonstrate this. Let's just say that the mass that we're working with here, let's say the mass was 15 kilograms, and the acceleration due to gravity, that's 9.8. So therefore the weight in this instance is just 15 times 9.8. And you get something like 147 newtons. So this weight as 147 newtons, the force of gravity still equals the weight. And so if we were to calculate the normal force here with these proposed values of 147, and I don't know, let's say that the angle is 18 degrees. 147 cosine of 18 degrees you're going to get 139.8 newtons. So tilting the mass, the weight stayed the same, but the normal force exerted by this surface was a little less. Yes, Troy?
Okay, I estimated when I was using this, you can see that I'm at a relatively steep angle and it's still staying on mostly, but then it starts falling off. I'd say that's about 80 degrees-ish. But the tangent of 80 is 5.671. And I'm wondering, is that the coefficient of static friction? And if so, how come we've never encountered a static friction coefficient of greater than 1? Yeah, probably more like 70 degrees, but still, it's pretty large.
Let's see. The coefficient of static friction, if you do tangent of 70 degrees, that does give you 2.7 and a certain value there. It could be that the coefficient of friction there for your hand is really that high. And because coefficients of friction and if there are adhesive forces between molecules, then yes, the coefficient of friction can be greater than 1. So because of the oils on our hand or otherwise like the moisture, that probably increases the coefficient of friction. That's my guess. It depends on what kind of sweat for sure. Yeah, it depends on what kind of sweat is going on. Because if we're just thinking of sweat as liquid, our grip on wet objects is less than dry ones, which is why you are extra careful when driving during the rainy days, of course. Yeah, it depends on the type of sweat and the other conditions. All right, so now that we've looked at the y direction, what force would be causing the box to slide down the slope? So there's no push, there's no pull. Okay, yes, it's gravity, but remember the force of gravity is pointing down. So what part of gravity is going parallel to this slope? Exactly, we would be talking about the x component here of gravity. Troy, was your question about the box on here or was it on something else? If it is about something else, I would ask that we please save it for maybe after class. So we have the f of g of x in this direction. And does anything oppose this f of g of x? Aha, so if it's sliding, would it be kinetic or static friction? Right, so we would say that there is some value of kinetic friction opposing the sliding down of the box. So if we are using Newton's second law and looking at all the forces at play on this particular box, given starting information we can algebraically calculate other values. Now, I do want to talk about another scenario regarding boxes on inclines, because boxes on inclines also can apply to going up the incline, not just down the incline. So let's say we have some box again, and I just keep drawing boxes because they're simple to draw. So here is somebody pushing this box up a slope at some angle. And we still would say that the weight of the box, force of gravity, is downwards. And therefore, as a result, we can break up the force of gravity into components, where you have the y component and the x component. So you have f of g of x, and you have the f of g of y. We have the normal force, as always. We have the person pushing. And notice that, is gravity acting against the push, or is it acting with the push? Exactly. So just in this two-dimensional scenario, we can see the force of gravity acting against the push. Are there other forces acting against the push? Right. As Troy points out, there is friction as well. And so with the second law set up here, on the sum of forces equal to the mass of the object multiplied by the acceleration of the object. All the mass is here in this horizontal direction. And if we talk about, oh, this is the positive direction, this is the negative direction, we could say that you have the force of the push minus the force of friction minus the force of gravity in the x direction equal to the mass of the box times the acceleration of the box. So we're just looking in the horizontal direction for this second law analysis. Does anybody have comments or questions either about pushing something up a slope or something sliding down a slope as compared to just an object sitting on a flat surface? All right, so what Troy mentioned earlier about the tangent of theta, I'd like to examine with you all where that comes from. And when we look at on your own 6.9 on page 202, we have some object at an angle theta. And as always, we have the force of gravity. We have our normal force. My arrows are a little sloppier because I'm not using my ruler. We have the y component here and the x component. We have the angle theta. And we are told that there is some kinetic friction as well. The mass of this object is 10 kilograms. The acceleration due to gravity is 9.8 meters per second squared in the negative direction. The angle is 22 degrees. And we are also told that the change in velocity is 0, which means that the acceleration of the object is 0. So therefore, when we look at the horizontal forces here as it's sliding down the incline, the sum of all the forces is going to equal what value? Yeah, it's going to be 0. So Troy, if an object is at some constant speed, it clearly is moving. So when we say that the sum of all the forces on an object is 0, that doesn't automatically mean that something is at rest. It just means that there's no acceleration. Correct. So in our plan here, we're saying the sum of all the forces is equal to 0. That means you have your F, the force of gravity in the x direction, and we'll just say, oh, this is the positive direction, this is the negative direction. The force of gravity in the x direction minus the force of friction is equal to 0. So if we add the force of friction to both sides, what we're saying is that the force of gravity in the x direction equals the kinetic friction force. So this, again, this setup here is all due to the second law of motion. Does anybody have comments or questions about how we're applying the second law of motion? So when we take a look at f of g of x and the friction force, we know that the friction force is equal to the coefficient of kinetic friction multiplied by the normal force, right? That's just basically our formula. Because static friction is stronger than kinetic friction, stronger. I mean, you're probably thinking of the coefficient of kinetic friction versus the coefficient of static friction. And because the normal force is the same in both, then yes, the friction force from static friction is usually of a greater value. And when we have this normal force, do folks remember what we said about its values? Remember, we said that the normal force is equal to the force of gravity times cosine of theta. That's right. So we could say that the friction force is the coefficient of kinetic friction multiplied by the force of gravity cosine of theta. And for f of g of x, notice here, if f of g of x is this side of the triangle, are we going to use sine or cosine if the angle is here? And then we want to find out the value of this side length. Exactly, we want to use sine. So that means the force of gravity in the x direction is equal to the force of gravity times sine of theta. So if we take these two expressions and we say the force of gravity times the sine of theta equals the coefficient of kinetic friction times the force of gravity cosine of theta, what happens to the force of gravity, mathematically speaking? Exactly, it cancels out. So there's nothing wrong with calculating the weight as 10 kilograms times 9.8. The weight is 98 newtons. But mathematically, it cancels out, so there really wasn't a need for it. Because we're trying to solve for the coefficient of kinetic friction. You have the force of gravity times the cosine of theta. That cancels. Force of gravity, cosine of theta. That cancels. And we end up with the coefficient of kinetic friction is equal to the sine of the angle divided by the cosine of the angle. Now you will remember that sine of the angle is equal to the opposite side divided by the hypotenuse. The cosine of the angle is equal to the adjacent side divided by the hypotenuse. And the hypotenuses go away. And so you have the opposite divided by the adjacent, which is the same as the tangent of the angle. So we can simplify this to say u sub k is equal to the tangent of 22 degrees. Should we memorize how to derive all this, or can we just memorize that it's the tangent of the angle? Well, memorizing that the coefficient of kinetic friction is the tangent of the angle is useful. I'll be careful though, because you have to have the situation be exactly like this in order for that to happen. Right? Because again, you have the forces equal to 0. And so then you have the force of gravity equal to the friction force. Depending on the information that's given, that may not always be the case. So be careful. It's very tempting to just say, boom, boom. Always the force, the coefficient of kinetic friction is the tangent of the angle. But if you have a non-zero total force, that's going to add in something else to your calculations. So I could say this is useful, but don't make it some sort of rule. And when you have the tangent of 22, of course, you should get something like 0.4. Yeah, my calculator gives me 0.404 for the coefficient of kinetic friction. Maybe your calculator gives you something slightly different. Any comments or questions about what we did here in our plan? The calculation step was really short. Well, yes, that is what you get if you put in the tangent of 80. So it could be there that the material of the material of that book plus the oils on your hand or the sweat of your hand are causing the kinetic friction force or the static friction coefficient to be such a high value. Yes, Troy?
Is there a mathematical relation between the coefficients of kinetic friction and static friction, so that if we know one, we can just immediately calculate and know the other?
I don't know.
Because that would be very helpful. And if Weil knew about that, I think you'd probably want to throw that into his textbook.
I don't know if there's any ratio of the coefficients of static and kinetic friction. They're usually determined experimentally. So the way that this curriculum works is they always give you both of them, or if you're asked to solve for one of them, you're given all the other information. So there's no need to figure out like a mystery coefficient of friction if you only have one or the other. Good question, Ezra. So Ezra is kind of raising the issue of material science. Like if there is a certain material, shouldn't it always have a coefficient of friction? And the answer is, I haven't studied, I haven't studied friction in depth. So if you consider the asphalt road, like the typical example of just driving, you have the asphalt road, you have the rubber of the tires. All sorts of things can change the traction of a tire on the road. Is the road raining? Does it have rain on it? Is there mud on the road? Is there snow on the road? Is there oil on the road? How is the tread of the tire? All these things. So even though the asphalt itself may have a static value for the coefficient of friction, all these other materials will change ultimately the relationship between how the rubber of the tire interacts with the asphalt. But yes, we can go over another one. Let's take a look at on your own 6.8 here. So on your own 6.8, we have a 45-degree angle. That's probably a bit big for 45 degrees. I'm going to change it. There we go. So there's your angle. We are told that the mass of this is 45 kilograms. And the coefficient of kinetic friction, we are told, is 0.3. What is the acceleration of the block? So a block. What is it? Okay, so let me draw our box. And as always, we have the force of gravity. And we have our components to that force of gravity. And you have this as your 45-degree angle. You'll have the normal force. This is the X component of gravity. Here's the Y component of gravity. And then we have coefficient of kinetic friction opposing that. So now we have our plan. So we're looking at the sum of the forces is equal to, do we have a zero value here? No, we don't. So in this case, if it's not a zero value, it's equal to, right, so our unknown acceleration multiplied by what value? So we're trying to find out the acceleration of the block. We don't know what that is. Right, multiplied by 45 degrees. Sorry, 45 kilograms. So the sum of all the forces is going to equal 45 kilograms times our unknown acceleration. So what are the forces in this X direction? Right, so as Ezra points out, we have the friction force. We'll just say this is the negative direction, and this is the positive direction. And we have the force of gravity in the X direction minus the force of kinetic friction is equal to our 45 kilograms times A. Now, for the force of gravity in the X direction, we know that this is equal to the force of gravity times sine of 45. And then for the kinetic friction force, we know that this is the coefficient of kinetic friction times the normal force. And you have this 45 kilograms times the acceleration. Now, we can do some side calculations here. We can say, oh, the force of gravity, that's going to be equal to the mass times gravity, which in this case is 45 times 9.8. And when we take 45 times 9.8, we get 441 newtons. So we could take this value, this is our force of gravity, and plug that in here. And then how are we going to calculate the normal force again? That's right. So back on our sketch, we have the normal force is equal in magnitude to the y component of gravity. So if the normal force equals the y component of gravity, that means that this is the force of gravity times cosine, not sine. Cosine of 45 degrees. And we could solve for that right now, because you have 441 cosine of 45. And we get something like 311.834 newtons. So as we keep plugging things in, we can do the same here for f of g is sine 45. And really, sine 45, cosine 45, they give similar values because it's a 45, 45, 90 right triangle. So you have this 311.834 newtons minus 0.3, because that was our coefficient of kinetic friction, times 311.834 newtons is equal to 45 kilograms times A. You can divide both sides by 45. What is our final result? Okay, Ezra proposes 4.85. Any agreements or disagreements? And again, what we had here, this was our setup and our sketch. We had our plan, and then here we had our calculate. All right, Troy agrees, Sophia agrees. Yep, so your calculator should probably give you something like 4.851 meters per second squared for the acceleration of this object down this 45-degree slope. Where do we get the 0.3? That's correct. So this is part of our setup. So as we read the question on your own 6.8, we see that the coefficient of kinetic friction is 0.3. So that's why each step here is important. If you have a good setup, you can see all the forces and you have the given pieces of information. Think about your plan so that you know which equations to use. And then the calculation is easy. Is there something else we can clarify about on your own 6.8? Okay, seeing none. So you can see that tomorrow is a dedicated, this is chemistry, not physics, sorry. Tomorrow, we are applying Newton's second law to more than one object at a time, but we do have a dedicated day for practice and review. So we'll practice some of what we went over today, tomorrow as well, and then there's more review on Wednesday in practice. So please bring any questions that you had about objects on inclines tomorrow. And we'll pause here for today. See you on Tuesday, everybody. Have a good day.